are going to go over the three response questions to the Chapter 4 practice test. Okay, so looking at number 7, we have a uniform 0.122 kilogram rod that is used to balance two masses. We want to see at what distance x should the 0.2 kilogram mass be placed to achieve static equilibrium. Okay, so here we are dealing with a torque problem, okay, because we're trying to balance this bar using our 0.5 and our 0.2 kilogram mass. So a good first step for these torque problems is to figure out what objects are trying to make your rod rotate and in what direction is each object trying to make that rod rotate. Okay, so if we look at our handy masses, we have this 0.2 kilogram ball. So that 0.2 kilogram ball, if that was the only thing on that rod, it would want to pull its end down, causing the other end to go up. Okay, so that 0.2 kilogram ball would make our rod rotate counterclockwise because its side would go down and the other side would go up. On the other side, we have this 0.5 kilogram ball. If that 0.5 kilogram ball was the only thing acting on our rod, it would want to pull its end down and the opposite side up. So it would make that rod rotate clockwise. Okay? So we've looked at the two objects that are attached to our rod. Now we need to look at our rod itself. So something to keep in mind here is that the fulcrum or that pivot point is not at the center. And if that fulcrum or the pivot point is not at the center, then we're going to have torque from the rod as well. Okay? So now we need to think, if that rod was the only thing on that fulcrum, if we didn't have either ball, the longer end, our left side, that's 0.65 meters, that one's longer, so that side would move downward, causing the other side to go up. So the rod itself, if nothing else was attached to it, would want to rotate counterclockwise. Okay? Because if we look at it, the majority of the rod is on the left-hand side, so that side is going to be heavier, pulling the left side down and the right side up, rotating counterclockwise. So then when we get to this point in our torque problem, we see what direction each object is going to make that rod rotate. Now we can set our counterclockwise torques equal to everything trying to make it rotate clockwise. Okay, because if we're in equilibrium, everything making it rotate counterclockwise has to be equal to everything making it rotate clockwise. So if you guys remember, our equation for torque is going to be our radius times our force sine theta. For the radius, that's the distance between the force and the pivot, or in the fulcrum. Okay, so if we look at our things making it rotate counterclockwise, we have our 0.2 kilogram ball and our rod itself. So since we have two things making it rotate counterclockwise, we want to add those two together to equal everything making our rod rotate clockwise, which will be our 0.5 kilogram ball. Okay. So if we look at our 0.2 kilogram ball, okay, we don't know our radius. Okay, we don't know how far it is from that pivot point. So our radius for that 0.2 kilogram would just be x. Okay. We need to multiply that radius by the force that ball is applying to our rod. Okay, so the force from that ball that would want to make the rod rotate is going to be the weight of the ball, and we know our weight is the same thing as force of gravity. So we would want to find the force of gravity that ball is applying to our rod. And we know to find force of gravity, we do 9.8 times our mass, which in this case is 0.2. Okay. Since it's a force of gravity, we know force of gravity points straight down. So if force of gravity points straight down, that is going to make a 90-degree angle with our board. So then we would need to multiply our force by the sine of our angle, or the sine of 90. Remember, the sine of 90 just ends up being 1, so if you want, you can leave that out. Okay, so to that, we need to add the torque from the rod, because both are making our object rotate counterclockwise. So we need to find the radius for our rod. So when we are finding the radius for our rod, what we need to do is find the distance from the center of the rod to the fulcrum. Okay, so we're basically saying how far off center is that rod itself? Okay, how far away is it from being equilibrium? So if we look at a rod, we know our whole length is 0.65 plus 0.25 or 0.9 meters. Okay, that means half of the length, or to the center of that rod, that has to be 0.45 meters. Okay, so it's 0.45 meters to the center. Okay, which means our fulcrum is going to be 0.2 meters away from that turning point. Okay, because if it's 0.65 meters from the left end to the center, or sorry, to the fulcrum, and it's 0.45 meters from the left end to the center, that means it's going to be 0.2 meters from the center to that fulcrum. Okay, so again, if we're not at equilibrium, we need to figure out how far off center that rod is going to be. Okay, and we can see that the center of our rod is 0.2 meters away from that turning point. Okay, so then we need to multiply that radius by the force that would cause that rod to move on by itself. It would be the weight of the rod that would cause that left end to move down. So again, we're looking at force of gravity. And we know when we find force of gravity, we do 9.8 times our mass. In this case, our mass of our rod is 0.122. Okay, so we would multiply 9.8 times 0.122 to find the force of gravity on the rod itself. All right, then we would need to multiply that by sine theta. And again, force of gravity is pulling straight down. So that would just end up being 90 degrees or 1, so we can leave that out if we want. Okay, so from here, we added together two counterclockwise torques. So those two objects that would cause a rod to rotate counterclockwise, and we need to set that equal to everything, make it rotate clockwise. So that's going to be our 0.5 kilogram mass. So again, we'll take our radius times our force times sine theta. Here, our object is 0.25 meters from that fulcrum. Okay, so 0.25 is going to be our radius here. Okay, it's always the distance from your object to that fulcrum. Okay. For our force, again, it's the weight of the ball that would be pulling down. Okay, so we need to find our force of gravity on that ball, again, by doing 0.5 times 9.8, our mass times 9.8. And again, we multiply that by the sign that the force is being applied. If it's force of gravity, it's just going to be sine 90 or 1, so we don't need to include that here since we're just multiplying by 1. All right, so from here, it just becomes an algebra problem to solve for that radius, okay, or how far away that 0.2 kilogram ball is from the center. 39 is equal to 1.225, subtract 0.239 from either side, divide by 1.96, and we should get that our 0.2 kilogram ball has to be placed 0.5 meters from that fulcrum. All right, let's go ahead and look at the next one. Incline. We know frictional force of 110 newtons exists between the block and the incline. We want to find the minimum force that would need to be necessary to move the block up the incline with a net force of 0. Okay, so when you see this net force of 0, that means we're in equilibrium and our forces are balanced. So net force is just another way of saying the sum of our forces. Okay, so 0 newtons means the sum of all of our forces is equal to 0. We're balanced and we're in equilibrium. Okay, so a good first step for these is always to draw your free body diagram. So we know we'll always have gravity pointing straight down. We know our normal force points perpendicular to our surface. So in this case, that'd be up and to the right. Okay. If we're being pushed up an incline, our applied force is going to be pointing up our incline here or up and to the left. And then since we do have friction, Friction always points in the direction opposite of motion. So here friction would be pointing downhill. Since we're moving uphill, friction will be pointing downhill. Okay, so if we look at this, this is where we have a free body diagram on an inclined plane. So this is that one scenario where we want to rotate our axes. So remember, we're going to say our normal force lines up with our y-axis, and our uphill, downhill, our applied force and our force of friction line up with our x. So that means it's just the force of gravity that's at an angle. So since force of gravity is at an angle, we need to break that up into its y and x components. Okay? So remember, always continue down that force of gravity from your normal force to get your FGY. Okay, how much of that force of gravity is pulling straight through your ramp? Okay, and then you can bring it over to your FGX, figure out how much of that force of gravity is acting directly downhill. Okay? Remember, the reason why we want to do that is because now that upper angle of our triangle, we can say is equal to our angle of incline. So that upper angle is also 35 degrees. Okay. So if we look at our relationships here, okay, we want to figure out what forces are going to be equal to one another since we are balanced. If we look uphill, downhill first, we can see we only have one force pointing uphill, that applied force. Okay, we only have one force pointing uphill. If we look downhill, we can see we have this force of friction pointing downhill and our force of gravity in the x direction. Since we have two forces pointing downhill, we would want to add those together to equal our one force pointing uphill. So on our x-axis, we have our applied force uphill is equal to our force of gravity x and our force of friction downhill. We can also look along our y-axis, okay? We can see our normal force is pointing straight up from the ramp, okay? So it's pointing up and to the right. If we look at what forces are pointing in the opposite direction along our y-axis or straight down through the ramp, we're going to see we only have our force of gravity in our y. Since we only have one force acting in either direction, we know in this case our normal force and our force of gravity in the y direction have to be equal to one another. Okay, so now let's start looking at our problem. We want to find what minimum force would be necessary to move the block up the incline, okay, if we're in equilibrium. So we are trying to find our applied force. So we know if we want to find our applied force, we need to know our force of gravity in the x direction and our force of friction. Luckily, they already told us our force of friction is 110 newtons. Okay, so we already know that force of friction is 110. So we just need to find the force of gravity in the x. Okay, so we want to know this component of our triangle. We know our angle, but we need to know the value of another side. If we look at our problem, we know the block has a mass of 15 kilograms. If we know our mass, we can multiply that by 9.8 to find our force of gravity. So if we do 15 times 9.8, I can find that my force of gravity is 147 newtons, and I can put that on the hypotenuse of my triangle, or for the value of my actual force of gravity. A force of gravity, or the actual value, always goes on the hypotenuse of your triangle. Okay. So now if I know my hypotenuse and I know my angle, and I'm trying to find the opposite side, I can use sine of 35 is equal to FGX over my hypotenuse or my force of gravity of 147. So if I want to find my force of gravity in the x direction, all I have to do is multiply each side by 147. And I'll find that my force of gravity acting downhill or in the x direction is going to be 84.32 newtons. So now that I know my force of gravity pulling downhill, I can add that to my force of friction to find what applied force needs to be acting uphill so that we are in equilibrium. And when I do this, I'm going to get an applied force of 194.32 newtons. Okay. If you look at our options, we can see they only use two sig figs, so we're going to choose option D here. Okay, so just like how we would on a normal surface, look to see what forces are pulling in either direction. And all the forces pulling one way have to equal all the forces pulling the exact opposite direction if we are in equilibrium of the chandelier. Again, always a good idea here is to draw a free body diagram first. So here we're going to have our force of gravity pointing down, force of tension going up and to the right, and force of tension going up and to the left. If we have forces at an angle, it's always a good idea to break them up in their horizontal and their vertical components. How much is pulling to the side and how much is pulling straight up. If we look at our relationships here, horizontally, we have one force pulling straight to the right, one force pulling straight to the left. So those two horizontal components of our tensions have to be equal to one another. If we look vertically, we have one force pulling down, our force of gravity, and we have two forces acting vertically. The y component of either force of tension, that vertical component. Okay. So since I have two forces pulling vertically, I'd want to add those two y components together to equal my force of gravity pointing down. Okay. So now that I know my relationships, now I can start looking at some values. So I know my leftward tension has a value of 427. I know my rightward tension has a value of 270. We're also given the value of the angles. Be careful as to where you put the angles, triangles them. We can use some geometry to know that if this angle here is 42, that means this angle over here is also going to be 42 degrees. And likewise, if this angle up here is 62 degrees, this angle down here is going to be 62 degrees. Okay. If you would rather solve for this angle up here, that's totally fine. Okay, because if we know if this angle is 42 degrees, then this angle, so that it adds up to 90. Okay, but whatever you want to do to help you get a value for your angle triangle. Okay, so if we look at this problem, our goal is to find our weight. Okay, so whenever it's looking for the weight, what you're really trying to find is the force of gravity. Okay. So we said if we wanted to find our force of gravity, we need to add our two forces pointing straight up. So we need to find the two y components of these triangles. So if we look at that left triangle first, okay, we know our hypotenuse is 427, and we know our angle is 62. So if we're trying to find the opposite side, we're going to want to use the sine of 62 is equal to that y component divided by our force of tension, or 427. So if we multiply each side by 427, we'll find that the y component of that left string ends up being 377.02 newtons. So we know that left string is pulling up with a force of 377.02 newtons. Okay. We now need to find with what force that rightward rope is pulling up with. So again, we're trying to find our opposite side of that triangle. So we're going to sine of 42 is equal to that force of tension in the right string and vertically divided by our hypotenuse, or our actual force of tension. And we would find that that rightward force of tension is pulling up with a force of 180.67 newtons. So now that I know my two vertical components, or my forces pointing straight up, I can add them together to equal my force of gravity pointing down. And I'll find that the force of gravity on the chandelier ends up being 557.69 newtons. Okay. And since my force of gravity is the same thing as my weight, that is my final answer. Always a good first step, draw your free body diagrams. Force of gravity points down. Here we have a force of tension pointing up and to the right. and the force of tension pointing to the left. Okay, so our goal is to find the tension in that horizontal cable. So we want to find the tension in our rope over here. Okay, so again, we have a force of tension at an angle. If we have a force of tension at an angle, we need to see how much is pulling horizontally and how much is pulling vertically. So we need to break it up into that triangle. Now that we have it broken up into its components, we want to see what relationship we'll have between our forces. If we look horizontally, we have one force pulling straight to the left, one force pulling straight to the right. So those two need to be equal to one another. Likewise, if we look vertically, we have our force of gravity pointing down, and we only have one other force pointing straight up. So those two vertical components need to be equal to one another. Okay, so since we only have one force pointing in either direction, balance one another out and be equal. Okay, so now that we know our relationships, we can start looking at our values. It tells us that the weight of our chandelier is 450 newtons. We just said our weights and our force of gravity are the same thing. So if our force of gravity going down is 400 newtons, that means the y component of this tension also needs to be 450 newtons. Okay? And we know if this angle is 60 degrees, that means this angle in the bottom of our triangle also needs to be 60. Okay. So we said our goal was to find that horizontal force of tension. And we said that horizontal force of tension was equal to the x component of my force of tension going to the right. Okay? So again, if we're in equilibrium, everything going to the left has to equal everything going to the right. So if we want to find the x component, we know our opposite side and our angle. We're trying to find our adjacent. So if we want to find the x component, that means we're going to want to use tangent, because we know our opposite is 450 and we're trying to find our adjacent. Okay? So to find the x component, or that horizontal component of our force of tension, we'll do 450 divided by the tangent of 60. And we'll find that our horizontal component is 259.81 newtons. That means if our x component, or rightward force, is 259.81 newtons, that tension in the horizontal cable also has to be 259.81 newtons. Only difference is that's going to be pulling to the left. So make sure you always add a direction to your force, okay? And we should actually add that, back in here. That should be 190 newtons uphill. Okay, so whenever you write an answer for a force, make sure you also include direction. Problem. So all these questions are based on a movie called Kingpin, which is a bowling movie if you've ever seen it. Okay, so number one, we're given some information, but the key idea here is that we are about to cut a wire, and that wire has a tension of 150 degrees or 150 newton at an angle of 150 degrees. What we want to do is we want to figure out which other wire, A, B, C, or D, we want to cut so that when we cut that 150 newton wire, our bowling ball remains in equilibrium. Okay? So we want to see which component, A, B, C, or D, will effectively cancel out us cutting the 150 newton wire. Okay. All right, so that we remain in equilibrium. So we know this wire has a force of 150 newtons at an angle of 150. But we know we typically work with acute angles, or angles less than 90. So when we make our triangle for that wire that we're cutting, instead of using the 150, we instead are going to subtract that from 180 to find our interior angle of 30 degrees. Okay, so the wire that we are cutting has a force of 150 newtons at an angle of 30 degrees. What we're going to be most concerned about here is the x component. Okay, because it's the x component that will cause the bowling ball to either tip to the left or to the right and fall on Mr. Munson. Okay? So we want to find the horizontal component of this force to figure out how much force are we removing. Okay. So if we want to find that horizontal component, we're going to want to use cosine. So say the cosine of 30 is equal to the x component over 150. Multiply each side by 150, and we'll find that the x component is 130 newtons, or 129.9. Okay, so we are getting rid of 129.9 newtons to the left. We now want to get rid of 129.9 newtons to the right to kind of even out our bowling ball. So we know we're not going to want to cut A, okay? Because if we cut A, now all of our forces are directed rightward and we're not in equilibrium. A component of 129.9 newtons to the right, that'll balance out the one that we're cutting, okay? So if we look at B, we know that that is 112.65 newtons at an angle of 64 degrees, okay? So that's our acute angle coming from the right. That angle there is 64 degrees. So if we look at wire B, we again want to find the x component because we want to balance out the one that we're cutting. So we say cosine of 64 is equal to our x component over 112.65. And we'll find that our x component here is 49.38 newtons. Okay, and we got that by multiplying each side by that 112. All right, since that is not equal to the force that we're getting rid of on the left, B is not the wire that we're going to want to cut. So now let's go ahead and look at C. So if we look at wire C, it tells us our force is 202.1 newtons at an angle of 50 degrees. So if we want to find the S component in C, do cosine of 50, which is equal to our adjacent, our x component over our hypotenuse of 202.1. And we'll find that our x component here is also 129.9 newtons. Okay, so that tells us we are going to want to cut wire C because it has the same horizontal component as the wire that we are already cutting. Okay, so cutting wire C will basically balance out or cancel out cutting that wire to the left because they have the same horizontal component. All right, so then looking at the next one, here we are on a frictionless ramp, and our goal is to find our angle of incline to keep our system in equilibrium or to keep Mr. Munson motionless. Okay. So if you look at this, we have two objects. We have our bowling ball and Mr. Munson and the sled. So we're going to want to draw two different free body diagrams here. If we look at the bowling ball, okay, we're going to have a force of gravity pointing down, and it's attached to a wire, so we're going to have a force of tension pointing up. And for an equilibrium, that tells us that force of tension and that force of gravity have to be equal to one another. Okay? It tells us that the bowling ball has a mass of 50 kilograms. Okay? So if we know the mass of the bowling ball, we can multiply it by 9.8 to find our force of gravity. And we find that our force of gravity on that bowling ball is 490 newtons. And if we have 490 newtons pointing down, that means we need to have 490 newtons pointing up with that force of tension. What's useful here is that the pulley, remember, does not change the value of our force. So that means our force of tension here has to be equal to our force of tension there because we're at the same rope. All it's being done is it's draped over a pulley. So if we have 490 newtons on the left side of our pulley, that means we need to have 490 newtons on the right side of our pulley. So now we're given some information about Mr. Munson and his sled. So let's go ahead and draw our free body diagram there. Okay, so we always have gravity pointing straight down, and our normal force is always perpendicular to our surface. So here it's going to go up and at an angle. Our wire is going uphill, so we're going to have a force of tension up and to the left. And it tells us that it is frictionless, so we're not going to have a force of friction here. Remember, when we're on our incline, that's when we need to rotate our x and y axes so that our y lines up with our normal force and our x lines up with uphill downhill. So that means it's our force of gravity that we'll want to break up into our x and y components. Remember, always carry down the y component from that normal force. The reason why we want to do that is because now this upper angle of our triangle is equal to the angle of incline, or theta. Okay, so if we look at this free body diagram, we want to see what relationships we have. We have one force pointing uphill, that force of tension, and one force pointing downhill, our force of gravity in the x direction. Since we only have one force pointing either way, we know those two have to be equal to one another. Likewise, we have our normal force pointing straight up from the ramp and our force of gravity y pointing straight down through the ramp. So again, since we only have one force acting in either direction, we know they need to be equal to one another. Okay, so now we can start applying some values to this free body diagram. We said earlier that our force of tension does not change over a pulley. So that means we're going to have a force of 490 newtons through that rope. We're also given some information about our mass. Mr. Munson has a mass of 100 kilograms, and the sled he's on has a mass of 110. So we know we take our mass times 9.8, we'll be able to find our force of gravity. So 9.8 times our total mass of 110 kilograms, and we'll find that our force of gravity is 1,078 newtons. Okay. If our goal is to find the angle of incline, or the angle in our free body diagram, we already know our hypotenuse, or that force of gravity. We need to know another component of that triangle. Lucky for us, we know our force of tension pointing uphill has to equal that force of gravity x pointing downhill. So we know these two have to be equal to one another. Okay. Now if we look at that triangle, we know two of our sides, so we can use trigonometry to solve for that angle. Okay, we want to use sine because we know our opposite and our hypotenuse, and that will help us solve for our angle. Remember, if we're trying to solve for an angle, we're going to want to use the sine inverse to get the angle by itself. So just sine inverse of 490 divided by 1,078. And when we do that, we'll find that we need to have our inclined plane at an angle of 27.04 degrees if we want to keep this in equilibrium. Mr. Munson is going to try, Arnie McCracken is going to try and get Mr. Munson hit by the saw by dropping a 5 kilogram pound of money at a distance of 2 meters from the fulcrum. Okay, so this is going to be a torque problem. Our goal is to figure out how far from that fulcrum do we need to drop a 9 kilogram bowling ball to keep our system in equilibrium. So remember, if we're in equilibrium, that means that all of our torques trying to rotate our forward clockwise has to be equal everything trying to rotate it counterclockwise. So if we look at the bowling ball or the bag of money, when that bag of money lands, it's going to drop the left-hand side of the board and raise up the right-hand side, or make that board rotate counterclockwise. However, if we look at our 9 kilogram ball, it's going to drop the right end side of the board and raise the left end up, or rotate that board clockwise. Okay? So for clockwise torque, we have our bowling ball. And we want to set that equal to the torque from the money. Okay, so that I'm trying to rotate it counterclockwise. Okay? Remember, when we do our equation for torque, we're going to do our radius times our force sine theta, where the radius is the distance to the fulcrum that the force is being applied. Okay, so if we look at our bowling ball, we don't know the radius. We don't know how far from that fulcrum we're dropping the bowling ball. However, we do know that it's the weight of the bowling ball, or our force of gravity, that would cause that board to rotate. And we know we find force of gravity by doing 9.8 times our mass, or 9 kilograms. Since force of gravity acts straight down, that's a 90-degree angle. That's sine of 90, so we don't need to include that here since it's 1. Okay. We then want to set that equal to the torque from our money, or that object that would want to make that board rotate counterclockwise. Here we know our radius is 2 meters. Okay, we're dropping that bag of money 2 meters from the fulcrum. And again, it's the weight, or the force of gravity on that money, that would cause our board to rotate. And we find force of gravity by doing 9.8 times our mass, which is 5 for that bag. And again, we need to multiply it by the sine of our angle, which in this case, again, is sine 90, since force of gravity acts straight down. So from here, it just becomes an algebra problem. So we end up with 88.2 R is equal to 98. Divide each side by 88.2. And we should find that we need to drop that bag of money that bowling ball, my bad, 1.11 meters from the fulcrum in order to keep the system in equilibrium. Another torque problem since we have something on a hinge. Okay. So here, we are trying to find out how much tension is in this rope as we hold the net up. Okay, so as we're in equilibrium and we're not rotating. So our first step in these guys is to always look at what objects are acting on, in this case, our net that would want to cause it to rotate. So the first one is that rope. If we were to keep pulling that rope up, it would cause the net to move up and go counterclockwise. However, if we didn't have the rope and we just had the net standing there by itself, the net would fall down and cause our net to rotate clockwise. Okay, so if we're in equilibrium, that means our clockwise torque from our net has to be equal to our counterclockwise torque from our rope. Okay, so remember, our equation for torque is radius times the force sine theta. Okay, so if we look at our net, okay, remember, here the hinge is not at the center of our net, so that net on its own would want to rotate clockwise. That's why we want to look at the torque of the net here, because the hinge is not at the center. So when we look at the radius for the net, we want to see how far away the center is from that hinge. Okay, so how far off balance is that net? It tells us that the center of the net is 4 meters, or the center of mass of the net is 4 meters from the hinge. So our radius for the net is going to be 4 meters. Okay. So if we let go of the net, it would be the weight of the net that would carry it down. So that means it would be the force of gravity of our net that would cause it to rotate. And we know force of gravity is 9.8 times our mass. It tells us our mass of the net is 100 kilograms. Okay. And we need to multiply that by the sine of our angle. Okay. Since force of gravity always points straight down, a 60-degree angle with the ground. So that means we're going to do sine of our angle here, we're going to do sine of 60. Because our net is making a 60-degree angle, that force of gravity is being applied at a 60-degree angle. Okay, so we want to set that equal to the torque of our rope. So that torque that we have wanting to rotate counterclockwise. So if we look at that rope, we want it for a radius, we want to see how far away from the hinge it is. And if our net is 6 meters long, that rope is going to be 6 meters from our hinge, or from that turning point. Okay, we need to multiply that by our force. In this case, since we're looking at a rope, that's going to be a force of tension. Since it is not force of gravity, we do not need to multiply that by 9.8 here. We're just going to leave it as a force of tension because it is not force of gravity. Okay? And we need to multiply that by the sine of the angle that force is being applied at. So this is a little tricky. What we're going to have to do is we're going to want to find the angle that this rope is making with the net. We want to find this angle right here. Okay, so what we can do is if we break this net up into a right triangle, okay, we know the angles of a right triangle always have to add up to 180. Okay, so if we wanted to find this angle right here, what we could do would be 180 minus the 60 degrees in that bottom angle minus the 90 degrees from our right angle. Okay, so that means that our top angle has to be 30 degrees. Okay, so we know the top angle of this triangle has to be 30. Okay, but our goal is to find the angle that the rope is making with that net. So we need to find the supplement of that 30 degrees. Okay, so we know the top angle of the triangle is 30, but we're trying to find the angle the rope makes with that net. Okay, so here we have a nice straight line. So that means our angles need to add up to 180, their supplement. So if we want to find that missing angle, we would want to do 180 minus 30 and find that the rope is going to make a 150-degree angle with that net. So when we multiply that by the sine of our course, we're going to want to multiply by the sine of 150. Because that rope is pulling up at a 150-degree angle with regards to that net. Okay. So from here, again, it just becomes an algebra problem. Multiply everything on your left-hand side, and then divide by your 6 and divide by your sine of 150. And when we do that, we should find that the force of tension in that rope is 31.61 newtons. Okay, so there's a practice test. Please let me know if you have any questions on any of these free response questions. I'd be happy to help. All right. Thank you and have a great day.